Watch this heavy steel deadbolt slide into place. For centuries, securing a room meant sliding a thick piece of metal into a reinforced hole. But look at this glowing electronic node in the dark. Modern commercial security has entirely abandoned moving parts. This cross-section of a door frame and leaf shows exactly how this works. Instead of pins and tumblers, an electromagnet mounts to the frame, and a flat metal armature plate attaches to the door. They align perfectly flush against each other. When electrical current flows through the coil, it generates a magnetic field that fuses the two plates together. Because there are no interlocking mechanical components, there is zero physical wear and tear, even after thousands of daily cycles. It runs on very low voltage, typically 12 or 24 volts, yet that small continuous current generates a holding force capable of withstanding upwards of 1,200 pounds of brute force. Security has moved past the era of heavy physical barriers, replaced by a 24-volt circuit that holds tighter than a steel bolt. Relying entirely on electricity to keep intruders out creates an obvious vulnerability. If the power grid fails, the door unlocks. Engineers solve this through a concept called fail-safe design. A fail-safe device is intentionally built to instantly drop its hold and cease its primary function the exact moment it loses power. The stakes here are life and death. If a fire breaks out and shorts the building's electricity, a locked door would trap crowds inside. By defaulting to an open state, people can always push their way to safety. Prioritizing human escape over asset protection means a commercial lock's primary job is knowing exactly when to stop being a lock. Traditional mechanical locks rely on heavy springs and grinding metal, creating a harsh operational noise that often reaches 70 decibels. Magnetic locks, operating through non-contact engagement, run at a library-quiet sub-20 decibels. However, standard face-to-face magnetic locks have a structural weakness. If a sudden, extreme shock impact hits the door, a direct pull can sometimes break the magnetic grip. This top-down schematic illustrates the solution, the shear lock. The armature plate slides horizontally to interlock with a recessed magnet casing. Notice how force vectors hit the door. Because it locks in shear, parallel to the surface, the horizontal hold absorbs massive impacts while staying hidden. Superior architectural security requires mechanisms that absorb brute force, rather than rigidly resisting it. Electromagnetism does have one dangerous flaw. Cutting the power does not always mean the magnetic attraction instantly dies. This animated diagram shows the power line severing, but a faint, lingering magnetic field still holds the two plates together. This is called residual magnetism, a ghost field trapped in the metal. In an evacuation, a crowd might find an unlocked door frozen shut. Look closely at the armature plate schematic. Engineers embed a spring-loaded push-off button. As current drops, the spring violently ejects the door, breaking the residual magnetic field. Mastering an invisible force like electromagnetism occasionally requires engineering brute force mechanical failsafes to defeat the laws of physics themselves. For all its brute strength, a magnetic lock possesses zero internal logic. It cannot make a single decision on its own. Look at this network map. The lock relies on an external brain, motion sensors, keypads, and fire alarms. A sensor node lights up, sending a signal to the central panel, instantly cutting power to the lock. The network continuously calculates human proximity to grant release. The physical lock has evolved from a standalone barrier into an active, thinking node within a building's central nervous system. Modern architecture relies on frameless glass, a material that is essentially a structural contradiction. It is visually fragile, yet requires massive holding force to secure. Magnetic locks secure these fragile surfaces by distributing over 1,000 pounds of holding force evenly across a flat plate, avoiding the concentrated pressure points of a mechanical latch that would shatter the glass. We have moved from medieval physical denial, thick wooden doors and heavy iron bars, to a silent algorithm that calculates human movement in real time. Our buildings have become active participants in our safety, continuously calculating, securing, and failing safely to protect the flow of human life.